Good morning, students. I'm Dr. Betty, continuing with the nuclear chemistry lesson 7. In lesson 6, we looked at nuclear fusion, where we said this is a nuclear reaction in which lighter nuclei combine together, all are fused together to form a single heavy and more stable nucleus, and in the process, a large amount of energy is released. Examples which were given were combination of two deuterons to give one helium nucleus. We further looked at the conditions which were necessary for the fusion reaction to take place. And we said these were mainly two conditions: high temperature and high pressure. We said high temperature is needed in order to overcome the repulsive forces. And also we say that at higher temperature, both lighter nuclei gain kinetic energy. Another condition was high pressure. We also said that high pressure is essential so that collisions are more frequent. High temperature and pressure can only be obtained in the explosion of atomic bomb. However, it was observed that the sun and the stars, for them, have got high temperatures. We also looked at the origin of the energy of the sun, where we said in analysis of the spectrum from the sun, it was observed that the sun is made up of hydrogen atoms or protons, which fuse together to give helium nucleus and an emission of large amount of energy. This energy is converted into heat and light. We also made a comparison between nuclear fission and nuclear fusion, where we said that in both reactions, mass is lost. This loss in mass or lost mass can be converted into energy, which is released in the process. Then the differences, fission reaction take place in a heavier nucleus, which split into two lighter nuclei, while a fusion reaction for it, two light nuclei fused together or are fused together to form heavier nucleus. Another difference was fission reaction are carried out by using slow moving neutrons, while fusion reactions take place at higher temperature and pressure. We also looked at hydrogen bomb, where we said that this bomb consists of deuterium and tritium core surrounded by an atomic bomb assembly. And when the atomic bomb is detonated, An explosion takes place and high temperature and pressure are emitted. Today, we are going to look at radioactivity. Radioactivity is a phenomenon in which the nucleus of the atom of an element undergoes spontaneous and uncontrollable disintegration or decay and emits alpha, beta, or gamma rays. The spontaneous emission of radioactive rays from the nucleus of a radioactive element is called radioactive disintegration or radioactive decay of the element. Now let us look at the types of radioactivity. There are mainly two types. We have the natural radioactivity and the artificial or the induced radioactivity. Natural radioactivity is the type of radioactivity where you have an element like uranium, thorium, and others emit spontaneously alpha, beta, or gamma rays, and the new elements are produced. Example here, we have uranium-238, which disintegrates into a radioactive thorium-234 with an emission of an alpha particle. Then a radioactive 234 thorium disintegrates to give rise to an emission of a beta particle. So the second type is artificial or induced radioactivity. As the word induced, we use an appropriate particle to bombard a stable nucleus, which with a suitable projectile, the particle can be alpha particle, neutron, and other particles. This gives rise to an unstable radioactive nucleus. An example is the aluminium-27. When bombarded with an alpha particle, gives rise to an unstable radioactive isotope of phosphorus-30 and emission of a neutron. Then the unstable radioactive disintegrate to give a stable silicon-30 and emission of a positron. Differences between natural and artificial radiation. Natural radiation is spontaneous since the nuclei of the heavy atom disintegrates on their own, while artificial radioactivity is not spontaneous since the nuclei of the atoms have to be bombarded by fast-moving particles. These particles can be alpha particle, neutrons, you can name them. Natural radioactivity is uncontrollable and hence it cannot be accelerated by any means, while the artificial radioactivity can be controlled by controlling the speed of the bombarding particles. Natural radioactivity is usually shown by heavy elements, while the artificial can be induced even in lighter elements. Let us now look at the units of radioactivity. The standard units of radioactivity is Curie, which is the quantity or the mass of radioactive isotope, which decays at the rate of 3.7 times 10 to power 10 disintegrations per second. Another one is Rutherford, which is the mass of radioactive substance, which produces 10 to power 6 disintegration per second. The point to note here is that 1 Curie is equal to 3.7 times 10 to the power 4 Rutherford. So divergence and the cell group displacement law. This law tells us about the nature and the new periodic position of the element produced. A radioactive element which loses an alpha particle is called a parent element. And the one which is formed or produced after the loss of the particle is called the daughter element or the daughter product. Emission of an alpha particle. An alpha particle is the helium nucleus whose atomic mass is 4 and the atomic number is 2. When a radioactive element emits an alpha particle, the mass number of the daughter element is decreased by 4, and the atomic number gets decreased by 2 units. Due to the decrease in the atomic number by 2 units, the daughter element shifts 2 places to the left in the periodic table, as in the given example. Emission of a beta particle. A beta particle is an electron which has mass number equal to 0 and the atomic number equal to -1. When a radioactive element emits 1 beta particle, the mass number of the daughter element remains the same because the beta particle, the mass number is equal to 0. But its atomic number is increased by 1 unit because the atomic number of the beta particle is -1. Due to the increase in the atomic number by 1 unit, the newly formed element or the daughter element gets shifted 1 place to the right in the periodic table. An example is sodium-24 with atomic number 11 disintegrates into magnesium-24 with the atomic number 12 with an emission of a beta particle. So there is an increase in the daughter cell of the atomic number by 1. Emission of a positron. A positron has mass number equal to 0 and its charge or atomic number is +1. And when a radioactive element emits a positron, the mass number of the daughter element remains the same because the positron, its mass number is 0. But the atomic number is decreased by 1 because it has a +1 atomic number. Due to the decrease in atomic number by 1 unit, the newly formed element gets shifted 1 place to the left in the periodic table. An example is magnesium 23 with atomic number 12 disintegrates to give sodium 23 with atomic number 11 with an emission of a positron. Addition of an electron or electron capture process. In this process, an electron from the K or L shell is captured by a proton of the nucleus. In this process, a neutrino is also produced. Here, an example is iron 55, which captures an electron to give rise to the formation of manganese 55 plus an emission of a neutrino. One of the 26 protons captures an electron and is converted into a neutron. And this process, one neutrino is also produced. The number of protons, that is the atomic number of the daughter element, is decreased by 1 unit. And the number of neutrons is increased by 1 unit. Consequently, the mass number remains the same. Let us look at the activity. The radioactive thorium-234 disintegrates to give lead-206 as the final product. How many alpha and beta particles are emitted during this process? The answer to this activity, we have to assume or to let the alpha particles to be X and the beta particles to be Y, which are emitted in the disintegration of 234 thorium nucleus, leading to the formation of 206 lead as the final product. So this equation will be presented as thorium-234, which emits X alpha particles. So this will mean that the atomic mass of thorium will decrease by 4x. So the atomic mass will be 234 minus 4x, and the atomic number will also increase by 2x, which is 90 minus 2x, leading to the formation of the element A. Then element A disintegrates to emit Y beta particles. So again, since beta particle is having 0 atomic mass, therefore the atomic mass of the final product, which is lead, will remain the same, which is 234 minus 4x. But the atomic number will increase by Y, which is equal to 90 minus 2x plus Y, giving rise to the formation of the product, which is 206 lead with atomic number 82. So equating the atomic mass 234 minus 4x to be equal to the final product of lead 206, and evaluating the value of x, we shall get x as 7. Similarly, equating the atomic number of the final product to 82. This will give us 90 minus 2x plus y. Since x is equal to 7, so we substitute for x, and we shall get the value of y as 6. Therefore, 7 alpha particles and 6 beta particles are emitted. So I can leave you with this assignment. With the above knowledge in slide 12, we will be able to answer this assignment. In the following natural radioactive series, where only the first and the last element are given, calculate the number of alpha and beta particles emitted in the following cases. The first one is uranium-238, disintegrating to give 206 lead as the final product. Thorium-232, disintegrating to give 208 lead as the final product. Another one is uranium-235, disintegrating to give lead-207 as the final product. So you are requested to calculate the number of alpha and beta particles emitted in each case. So next time, we shall begin with defining the half-life or half-life period of a radioactive substance.